Welcome to tutorial 12. This tutorial we're going to be looking at the 555 Astable oscillator. This is possibly the most important circuit that you will have to do in your GCSE AQA electronics course, both from a practical point of view and from a theoretical point of view for your exam. You will need to know how to draw the whole circuit, need to know the numbers of all the pins and their names. So let's have a quick look at the circuit and see if there's an easy way to understand it. First of all, we have R1, R2 and C1 in a series circuit with our threshold and trigger, pin 6 and pin 2, which have been joined previously together in the IC buffer, connected between C1 and R1. Pin 7 is our discharge pin, and that connects between R1 and R2. Pin 8 is our supply going positive. Pin 1 is our supply going to 0 volts or negative. Pin 3 as usual is our output. So when the output is high, in this case our LED will be on with our current limiting resistor 220 ohms. Now, two extra pins we've got here that we haven't used previously. Pin 4 is our reset pin. We'll look at what that does in a short while, but at the moment it's just going to be connected to plus 5 volts. And pin 5, well, most of the time it probably wouldn't matter if it was connected or not. It's our control pin. It's a voltage controlled oscillator pin, and we connect it usually to 0 volts via a 10 nanofarad capacitor. That's not hugely critical, the value, and in fact, as I said, we can get away generally without connecting it at all. But because it's part of the circuit diagram that the AQA course requires, I've put it in here for now. So what we're going to do, we're going to have a look at this circuit. We're going to be changing the values of R1, R2, C1, and having a look at what happens to our output, and we're going to be measuring it on the oscilloscope. We're then going to be using our formula for frequency in this circuit, which is 1.44 divided by R1 plus 2 times R2 times C. That will give us the value for formula. We'll have a look at a few other things as well. And the table that we're going to be using, we're going to be doing 4 different combinations of values. We're going to be starting with R1 as a 1K resistor, R2 as a 6.8K resistor, and C as our 0.1 microfarad capacitor. Okay, let's have a little look at the circuit. So there we have our circuit. I've already turned it on. The LED is flashing, but once again, it's flashing far too quickly for us to see, so we need to use our oscilloscope. So I'm going to turn my oscilloscope on. Generally, the most difficult thing is getting a trace that we can see. You can see that the line is at the bottom, so the first thing to do is to put it onto ground and move the line up to the middle, and then put it onto DC. Now we can see the line has moved up. That either means that there is no signal, or we are probably under such a microscope here that we're looking at only one part of it. So I'm going to change my time base, and there we go. We can see that we now have a on-off signal, and I can change this using the time base setting to whatever I find the most convenient. So I'm going to do it so I only see one waveform. Now, once again, we can't see a whole waveform here, so that's the setting that I need to go on. I can position it so that I can make my measurements easier. So I've started my waveform at the bottom here. I'm going to measure one waveform, which is a low plus the high. That is one waveform from there to there. So that is 1 division, 2 divisions, 3 divisions, 4 divisions. That is about 4.9 divisions if I'm going to try and be really accurate here. So let's enter that into our sheet. So I'm about 4.9 divisions. Now my time base setting is currently at 0.2 milliseconds. 0.2 milliseconds. So each division is worth 0.2 milliseconds. So if I multiply the number of divisions by the time base, that will give me the amount of time for one waveform. So I have 4.9 times 0.2 exponent milli is minus 3 equals 9.8 times 10 to the minus 4. Once again, press our shift engineering button, which gives us 0.98 times 10 to the minus 3. So in other words, 0.98 milliseconds. That's how long it takes for one waveform. So the frequency is 1 divided by time, just like time is equal to 1 divided by frequency. So if that is the time for one waveform, therefore 1 over that will give us the frequency. And I can use my x to the minus 1 button, which is like saying 1 over the answer. X to the minus 1 equals 1020. So what we're saying is it takes 0.98 of a second for one of those waveforms, and because it only takes that amount of time, it is flashing at a rate of 1020 times every second. So let's have a little look at our formula and see how we can fit this into our calculation and compare it to our answers. So already in the information sheet, it tells us that frequency is equal to 1.44 divided by R1 plus 2 times R2, and they need to be worked out first, times C. Now there are many ways of doing this. It depends how good you are with the calculator. So that equals 1.44 divided by 1k plus 2 times 6.8k, because they were the values we used in this experiment, times 0.1 microfarads. So that's the same as 1.44 divided by, and now let's work that out. So I want to work out 1k plus 2 times 6.8k first. So 1 exponent 3 plus, open my brackets, 2 times 6.8 exponent 3, close my brackets, equals, so that's 1k plus 2 times 6.8k is equal to 14.6k, times 0.1 microfarads, 0.1 exponent, micro is minus 6 equals 1.46 times 10 to the minus 3. Now you can use your memory button here. You can do this however you want. I've already written it down, so to keep this easy, I'm just going to cancel this and go 1.44 divided by 1.46 exponent minus 3, that value at the bottom, equals 986. So our calculation has told us that this circuit should have been flashing at the rate of 986 times every second, because that is 986 Hertz. Our results gave us a value 1020. So we're not too far out. We're about 34 Hertz out, which is fairly within tolerance here, given tolerances of components and our ability to read the answer on the oscilloscope. Let's do the next one. So I'm just going to enter that into my table. 986 286 hertz. So I'm now going to change R2 and R2. Let's just remind ourselves which value we're changing. We're changing the resistor between pin 7 and pin 6 and 2. R2 becomes a 3.3 k ohm resistor. There we go. So, looking at our oscilloscope, we can quite clearly see that the frequency has changed from what it was before, because I haven't changed any of the settings, yet I have far more waveforms on my oscilloscope screen than I did before. So, we're going to adjust our time-based settings till we get, there we go, that's probably the best setting. Going to position it so I can make my measurements easily. And I'm starting at the bottom, so I'm going from there to there. And I go 1 division, 2 divisions, 3 divisions, 4 divisions, 5 divisions, probably 5.1. So we now have 5.1 divisions. Each division is worth 0.1 milliseconds, so that's 0.1 milliseconds. Using my calculator, I have 5.1 divisions times 0.1 exponent minus 3 for milli equals, now it's given me it in times 10 to the minus 4, so let's go shift engineering, 0.51 milliseconds, and if I do my x to the minus 1 to give me 1 over that answer, which will give me the frequency, x to the minus 1 equals 1960. 1960. So in other words, this circuit is flashing at a rate of 1960 times every second. Each flash happens in 0.51 of a millisecond. Let's have a look at the calculated value on this one. So we know that frequency is equal to 1.44 divided by R1 plus 2 times R2, work that out first, times C, equals 1.44 divided by, what were our values? 1K plus 2 times 3.3K times the 0.1 microfarad capacitor. So therefore we have 1.44 divided by, well, we can do this easy. We know that 2 times 3.3 is 6.6K plus the 1K gives us 7.6K. So we can do that quite easily. 7.6K times 0.1 microfarads. Therefore, that equals 1.44. So 7.6 exponent 3 times 0.1 exponent minus 6 for the micro equals, shift engineering to take it away from the minus 4, which equals 0.76 times 10 to the minus 3. I leave it as minus 3 here because we're using our calculator. So 1.44 divided by 0.76 exponent minus 3 equals 1894 hertz is our answer. Let's have a look and compare that to our measured value. Well, that is not bad at all, 1894 hertz. So we measured it to be 1960. That's about 66 hertz out, which is still well within tolerance and what I'd expect. Okay, go away, do your measurements on these two, come back and I'll show you my results. Okay, let's have a little look at our results. So I finished off the last two, and hopefully you will find that in your experiments and your calculations you will get much the same answers. So our calculated frequency, which should be identical, you should have found that the third one gave us 464 Hertz and the last one gave us 266 Hertz. My measurements gave me 487 Hertz, which is about 23 Hertz difference, and then my last one gave me 270 Hertz, which was only 4 Hertz difference. You would have had to have changed your time-based settings for each of those readings. If we very quickly analyse those results, you will see that as we change the value of R2, so we halve the value of R2 here, we have almost doubled the frequency. Here we increase the value of R2 by about 5 times, keeping the same value as C1 and R1, and here where we have increased it, we have reduced the frequency, and by approximately a fifth. And then finally here, even though we are changing not only R2, we are changing C1, but C1 is significantly different. Perhaps that would be the best one. The second and the fourth one, R2 was approximately the same, R1 was the same, but C1 has changed by 10-fold. And you can see here that there's a significant difference in frequency where we have reduced the frequency. Okay, let's have a little look at the rest of the results here. So it asks us to show your working for one of the frequency calculations, and that would be what we've done on our sheets over here. Then it says what was the amplitude for one of the waveforms with the 220 ohm limiting resistor and the LED, and what is the amplitude for one of the waveforms without the 220 ohm resistor and LED. Well, if we have a look at our oscilloscope trace, our LED is currently in the circuit, and we can see from this trace the amplitude of the output. Now, we have been working on a horizontal axis looking at the time base, but we can do exactly the same by measuring the number of divisions upwards and then looking at how many volts per division are on our vertical axis. In this case, we can see that the dial is pointing to 2 volts for each division. So how many divisions upwards do we go? Well, currently it is 1 and about 1.8. So that is about 1.8 divisions up, and each division is worth 2 volts. So if we go up 1.8 divisions and each of them is worth 2 volts, that means that the amplitude must be 3.6 volts. If we look at this again, and now I remove the LED, which disconnects any output, you will see the output change on the screen. There we go. So now we can see that the output has changed to 2.2 divisions. 2.2 divisions. And we haven't changed the volts per division, so they remain at 2 volts per division. Therefore, the output without the LED resistor connected is now 4.4 volts. Because, of course, that would explain the experiments we've done before in terms of an LED having a voltage drop across it and drawing current from the output. And when you draw out current from the output of something, then the voltage will drop. Next question says, what happens when you connect the reset to 0 volts? Well, currently our reset was connected to the 5 volt supply. So I am now going to disconnect my reset from 5 volts. Let's see if I can show both. And as I pull that out, nothing has happened. But when I plug it into 0 now, you can see that the output has dropped to 0. This is our reset pin. So when the reset is high, it is not being used. But when we connect the reset low, that is when we are resetting the circuit and the output of a 555 Astable stops oscillating. If I connect this back up to high, in fact, as I remove it from 0 volts, you can see that it already starts oscillating again. In other words, it's not connected to 0, and it just recognizes that the wire is not connected to 0, so it doesn't matter about being connected high. But it is always worth putting pin 4 high so that it is not recognized as a low. But when it goes low, it is reset and the output of the 555 stops oscillating. Okay, I'd like to do one little bit of what I call extension work here, and I'd like to just analyse the mark space ratio and have a little look at the calculations that go with that. If we look at our waveform, a waveform is made up of 2 bits. It's made up of this area high, which is called the mark, and this area low, which is called the space. And the relationship between them, i.e. the length differences, if you like, is called a mark space ratio. And the time period is equal to the length of the mark plus the length of the space. And as we know, the frequency is equal to 1 over that whole time period. So if we go back to our original values, when we look at it, we worked out that the frequency would be 986 Hertz. But we had measured on the oscilloscope that the mark plus the space was 0.98 milliseconds. And therefore our frequency was 1020 Hertz. Sometimes it may be useful that you don't want an equal mark space ratio. And we can quite clearly see from our oscilloscope trace here that our space, mark, space distances are pretty even. I'm not going to measure them accurately right here and now, but we can see that they are fairly accurate to one another. But there is a formula, as I've given on the sheet, that allows us to work out the mark space ratios should we want. So in this experiment we were using R1 as 1K, R2 as 6.8K, and C is 0.1 microfarads. So in our first experiment we worked it out to be 986 Hertz from our calculated, but we measured it to be 1020 Hertz on our oscilloscope. So we're now going to look at a mark space ratio for that waveform, and we are given the formula that the time high, i.e. the mark value, TH equals mark, was 0.7 times R1 plus R2 multiplied by C1. So if I plug my values into my calculator here, I'll work out R1 plus R2 first. So we have 1 exponent 3 plus 6.8 exponent 3 equals times 0.7 equals times 0.1 exponent minus 6 for the capacitor equals. Shift engineering gave us a value of 0.5, I'm going to round that up, 55 milliseconds. And our time low, and there is our time low, which is our space, is given by the formula 0.7 times R2 times C1. And you will notice that the time low is not affected by R1, but the time high is affected by R1 and R2 and C. So 0.7 times R2, which was 6.8 kiloohms, times C1, which was 0.1 exponent minus 6, equals 4.76 to the minus 4, engineering, rounding it up, 0.48 milliseconds. So our time high plus our time low equals time high plus time low. We've already got time low in there, so I'll add 0.55 milliseconds. Gives me a value of 1.026 milliseconds. And that would give me a frequency of 1 over the time equals the frequency equals x to the minus 1 equals 974 hertz. And our calculated would have been 986, but we have been rounding up a little bit here, so that should have equaled that exactly. And our measured value was 1020, which is pretty close. But more importantly, here what we were trying to do, that is our time period for the low plus the high, the mark plus the space. And we made our measured time period from the oscilloscope in the first one 0.98 milliseconds, and here it's 1.02. So only 0.04 of a millisecond out, which is very small. This is the end of tutorial 12 and the Astable.